Good morning, Howard.
Good morning.
How are you?
Okay, coming up on the hour here.
Yeah.
I was just on a call on modular data centers.
Oh, yeah. Carl Ray.
Yeah. And sort of interesting application of lots of small scale, but in that same call, there was talk of AI scale, NVIDIA, and all that sort of thing, and megawatts.
Right.
Um, what's going to happen? The infrastructure needed to feed AI stream, applications where this gets going to be used more and more and more. And we're talking an incredible amount of wattage, power, energy, and the infrastructure that's in place today. It's really kind of scary.
It certainly is.
And I was on something yesterday and talking about the energy required for a Google search, just like, some search of some sort. And the very tiny amount of energy required to search those things out.
Oh, yeah.
Do
I think I
a
saw that
regular
post.
search. But an AI search, as we know, if you do something, it takes a long time for that to process, where a Google search on a little bit of nothing turns into, you know, you get a million responses in a half a second, right? But
Yeah.
if you request a image or a please, like your create a summary of the discussion today. It
Yeah.
takes a long time for that data to come back. And that's a single response instead of, 7 million Google responses to your question about how do I find a dentist near me, right? So, uh, the energy we have today in our data centers that's being consumed, and if it's 70 times as much energy, that we have be a little worried about our power infrastructure.
Yeah. That's
But
it. Although I guess they are saying that GPT 4.0 is actually, well, it's getting quicker. I don't know if it's getting lower power. I guess relative per token. I presume it's getting lower power. But yeah, big problem.
yeah. So you talked about in your note today that you were where's your note here? Do we have a representative?
Just the one I just sent out, you mean?
Yeah, just sent it out a minute ago. What
Oh,
did
I
you
just
say?
said continue our discussions on the new frontiers, basically.
New Frontiers, that's what it was. Looks like the connector group is well represented today.
Yeah, we've got a few people on. That's good. Let me just fighting with Google Docs. Let me in. Decided it sometimes randomly decides that it wants me to sign in just when you're in. It works fine until the meeting starts.
So you're in a hurry.
Until you're in a hurry. That's right. Good morning, Z, and good morning, Jason.
My name is Aaron. Good morning, everyone.
Hi, good morning, Aaron and everyone. Yeah.
Good morning, Z. Good morning, Jason.
Okay, I think we have a relative quorum. All right, good morning, and chaps. I think it's 8:04 I think we're probably got everybody that's going to join. So I don't have a lot for today in terms of from my input, except for I guess on the last core call that we have last Tuesday, I did say that I based on what I put forward on the OCP Regional Summit, the extra detail we went into, including the Universal Interconnect extra detail, I said that I was going to try and get that into the proposal, you know, sort of a top middle proposal effort. I've only really just started on that. I've been trying to. So one of the consistent feedbacks we've got is that, you know, we're presenting quite a technological step forward, you know, in terms of a re-architecture and redefining computing architecture from the ground up. But everybody says, you know, typical of, well, what's the use case? What's the, and what are we going to build is our reference platform. And you know, the idea is that we can build any machine, so it can cover any use case. Ideally, we'd want a customer and with a particular use case. And if we can drive it that way, maybe we can get a little bit more of a understanding and buy-in. If we can sort of really put numbers behind this approach. So I've been trying to change my tune a little bit on that top level side of things, which is obviously, you know, this piece, the interconnect piece, all of the individual efforts that we're trying to do across the silos are way down in the weeds compared to that, for sure. But just to give you an update on where my head's at, we've been talking about an FPGA HPCM module being a good starting point with an application of FPGA of ASIC emulation, which has always been a big industry for FPGAs, and it's sort of now owned, you know, lots of, including my company, lots of sort of companies that built various FPGA emulation platforms over the years, but it's now pretty much dominated by the three big guys: Cadence, Synopsys, and Mentor, or Siemens own Mentor now. And their machines are you know, increasingly expensive and very, very sophisticated. But I have heard ongoing demands or desires for, you know, for people to build their own emulation platforms. And when we look at where we're going, like we've got 80 billion transistors, I think, on the H100. And we're seeing that TSMC with the likes of Dojo and Cerebrus, we're going to wafer scale now. And when you add that up, we're talking many hundreds of billions of, if not approaching a trillion transistors in a wafer. And so you can imagine that you would like to emulate that. And I did some math on the FPGA approach. The biggest FPGA from AMD is actually roughly about 4 billion transistors it can emulate, 4 billion ASIC transistors it can emulate. So, you know, you divide a trillion by 4 billion, that's still thousands of thousands of FPGAs. So I mean, actually, in the numbers I've done, I remembered we would be in the order of certainly hundreds of FPGAs, and even if we were doing just a reticule size chip all by itself, not wafer scale, then we're still in the almost knocking the door of 100 FPGAs to be able to emulate that. And with the domain-specific approach as well, then where you want to wire these together in certain fashions as to the way the ASIC would ultimately be wired up, then having a very flexible interconnect between these FPGAs would be great. So I've been building more and more sort of weight behind the ideal application is FPGA emulation. And the nice thing about FPGAs is they have a lot of transceivers or certain devices, the bigger devices do. Like the largest one is for ASIC emulation has 160 transceivers on it. Not quite is up to the full 320 that we support on the HPCM, but it's a pretty good number. And so then it came to me about, well, the applications. And so the application wise, we've been talking about domain-specific computing architectures, which Hennessy and Patterson 5 to 10 years ago now actually we're starting to put more focus on. But if we think about high-performance computing, that very much is a domain-specific architecture historically, because really HPC has been what we call a nearest neighbor type compute. Like weather models, you've got atoms knocking each other next door. So it's all these processing. So they lend themselves to what we call a mesh architecture of just connecting between neighboring common compute devices. And things like quantum chromodynamics, nuclear fusion, or all of these classic HPC codes really lend themselves to what they call this nearest neighbor model, which gives you the old classic HPC. And then we look at AI, and AI is another domain-specific architecture. And interestingly, historically, we haven't really built domain-specific architectures at the big scale. It's been HPC, or you have these much smaller machines. Obviously, an iPhone, for example, is very domain-specific, and they put accelerators all on one piece of silicon, and the volumes are massive. So that is very much a domain-specific chip, but it's obviously all buried in one piece of silicon. And it's all about the power consumption. But AI is really a new kid on the block, well, relatively speaking, and it's domain-specific, and we've got trillions of dollars, literally, when you look across what everyone's doing, investing in making domain-specific processors and computers specifically for AI. And that's really our first venture since HPC, which has been going for many, many decades at the large scale. So, and Hennessy and Patterson are saying all of our computing for all of our applications, we need to build domain-specific computers now. So yes, we've done it for HPC because that massive need. Yes, we're doing it for AI because of that massive need. But we need it for other applications as well, if you follow Hennessy and Patterson's arguments. And then we need so we need some way of prototyping these new machines and getting to them where the market isn't so massive that people just throw billions and trillions of dollars at it. It's that we can actually build a machine and a domain-specific machine in a very cost-effective way. So this is sort of my if this makes sense. By the way, I'm sort of playing this by you guys. I know it's not interconnect specific, but I'm playing this by you guys just to see how well this rings true, in terms of me trying to deliver it, because I need to capture the attention of DOE with the opening paragraphs, and I'm sort of trying to articulate where my head's going. So, and one of my FPGA friends from good old Xilinx said, FPGA and ASIC emulation is a bit of an old name. We should be using digital twin. I don't know if you've been listening to NVIDIA, but digital twin is the new buzzword, right? And so we need to build digital twins of our new supercomputers going forward. So the HPCM wall of compute could be a digital twin machine where you build, just this massive array of FPGAs, and you make a digital twin of your wafer scale compute for a particular domain application, or your reticule size, or multiple different reticule size devices. And you can construct it quite easily with the wall of compute. You can interconnect all of those elements. in a very domain-specific fashion with all of our cable infrastructure and our close proximity for energy efficiency and budget allowance for sticking with copper where possible. And then as you get real ASICs, and this is included in the chiplet world, as you get real ASICs or real chiplets, you can actually unplug a module and plug in one of these physically built ASICs or chiplets into the emulation platform, into the digital twin, to have some real hardware inside the digital twin, but the pieces that are missing are still emulated in the digital twin. And you gradually introduce the real hardware and make sure everything still works in the emulation when you start to introduce real hardware. Something I used to do as a young man in the defense industry when we were building big missile systems. That was an approach. You'd have one big simulation and you gradually introduce real hardware and take out the simulation and replace it with real hardware, but the rest was still a simulation, and make sure that everything still worked, that there wasn't any errors in your simulation versus the real hardware. And so that would then allow you to gradually build this domain-specific machine out of the real devices as you created them and replace the FPGAs until you'd replaced all the FPGAs, and suddenly this HPCM wall of compute is all of these new dedicated ASICs, etc. And so that's the story. And then it basically came to, well, okay, that's a good story. Well, in my mind it is, so love to hear your feedback in a minute. But what is the killer application, this not AI and HPC, that really warrants a domain-specific computer to its exact needs, rather than just have to say, well, I'll have to leverage traditional HPC to do my world. It's not specific to my domain, but it's close enough for me to get some decent performance. And equally, with all the investment in AI, even the HPC people are saying that they're being left behind because there's too much focus on AI and everyone's forgetting about HPC. So the one that popped into my mind was because I've worked on it in the past, a couple of decades ago, with GE, was computational fluid dynamics, which is used just about everywhere. It's a massively used piece of code, relatively speaking, in terms of our engineering world, and especially simulating the thermal aspects of all of everything, etc. And the beauty about CFD is it's an extremely complex code. It's got a bunch of functions, disparate functions, where some of them might play nicely on a GPU, some might nicely on an FPGA, some maybe a dedicated ASIC would be good to be developed, and they are huge. Like I think GE just released a public paper on what they did on the Frontier supercomputer machine, fairly successfully or very successfully. But again, that machine was not necessarily particularly optimized for CFD, but they managed to get something performant. So because it's such a heterogeneous type of code base, and if you just accelerate the core hotspots, you just get maybe 2x acceleration of the overall application because of Amdahl's law challenges, then it sort of makes a lot of sense that might be an ideal candidate to, could we start with an FPGA emulation and work our way to a dedicated CFD machine? And so that was the target application that I was going to put as our first digital twin example that we could look at. Would this machine work for? So I've been sort of sticking my brain into that higher level aspect, as opposed to diving into the details of the lower level aspects like I did for the regional summit with the different work streams. And that's where I am right now. So how does that sound to you guys? Does it make sense? Does it ring true, or is it double Dutch, or what do you think from I mean, obviously you're interconnect guys, so maybe it's a lot of things I've described are not really in your core focus area, but just as a general story, how does that sound to you?
I think as a general story, it's a good fit. And as your story wandered around between what's happening at NVIDIA and what happened at GE, the picking what you called a killer application is probably the most important piece, because you have to find a place to park this thing to start with.
Right.
So, and the chiplets and FPGAs and that is above me. But the story that goes along with it, somebody's going to need a better understanding of the chip side of how this goes together. So there's chiplets, there's FPGAs, there's ASICs, there's what the future looks like for the massive, applications for what we had talked about earlier, like AI stuff that's going to draw an incredible amount of energy and computing power. If we have an application here that is on a much smaller scale or can do things better, and I think that's the selling point. This can do something better. And that's going to be where somebody's going to say, I'm just going to go along with everybody else, and here's the data center, here's whatever, and we're going to need to power this thing. If there's a selling point that this is smaller and more able to grow a little bit at a time. I don't know. I'm just sort of wandering about.
Yeah, I think the cost
thoughts here.
effectiveness, when I was explaining to somebody else, I was trying to get on board. I think the sheer cost savings, as well as the things like efficiency aspects of power delivery, thermal management. I think I think we have a tremendous opportunity for simplification in reducing the cost of the infrastructure. We need, well, in that sense, we sort of, that's what we need to do is get everything more aligned there. So I think that's an opportunity. But as somebody said to me, I mean, if you look at like what NVIDIA have done with Blackwell, although I use that in my regional summit, it's like, well, they'll get there organically eventually. They don't need to do your step change, Alan, which is a fair point. I mean, NVIDIA are beginning to get there. They've got rid of their motherboards now. They've gone to cables everywhere in their Blackwell machine. They're moving to direct liquid cooled. They're 50-50 right now. They've got their power delivery, their 120 kilowatt rack. Okay, it's got a lot of room for improvement, but they're making steps in that right direction. So maybe maybe their next iteration will be closer to our wall of compute, and it'll be proprietary to them, right? So that's what we're up against.
Yeah.
Now,
yeah, I think that this one is just think about the needs of the applications for future. And the other thing is, I think this idea is to provide flexibility and scalability to achieve the efficiency. Okay, but the other way, I think you consider the universal, then that will bring the challenge, to deny the architecture to fit all. So that's the two ways. One is you want to get the simplicity, okay, but the other way, if we move to the universal, then we need to think about the challenge.
I see what you mean. It's a bit of an oxymoron, universal and simplicity.
Yeah, both kind of is a two-way, right?
Yeah, I get your point. All right. Yeah.
We maybe think about the selected universal.
Yeah, I guess I mean that does bring us sort of back onto the interconnect piece.
Yeah.
I think in a lot of ways, at the end of the day, the simplicity of transceivers is they're all transceivers in my mind, and they're all pretty much exactly different flavors of something that's exactly the same. And in that sense, it's a case of, you know, if these separate fiefdoms like the Ethernet consortium in the PCI consortium in whatever InfiniBand in NVLink and all these other ones, right? If everybody just got in the same room and said, we can still do our, we could all sit on top of the same electrical and PHY layers. It would be beauty would be in its simplicity then, and then you just bring, you know, and that's what we're trying to do. We're trying to get that Lego block simplicity into the physical architecture to allow us to easily build any domain-specific computer. So, so I take your point. I mean, the challenge we've got as a group is our universality is trying to deal with the challenges of the physical differences of the Ethernet versus PCI, I guess, at the electrical, the thermal, the optical, everything. I mean, in my mind, it doesn't seem insurmountable. I think we want to keep a focus on beauty is in its simplicity. And I think the act of us doing this under this work stream is, whilst we might have a goal for this universality, you know, of, hey, we want to drive a copper cable 2 meters at the 224 gig, you know, there will be a thing where we might say, that's just not going to work. The only way to do 224 gig is with active cables. And okay, we say in our universal interconnect, once you get over 112, we don't have a passive copper solution because we can't do it. You need to go to other solutions like what NVIDIA have done if you want 224 over just copper with great big fat cables. So I'm sure we're gonna need it, but that's, I think, where this work group comes in. It's a case of how do we build universality while keeping the simplicity? And whilst we're at the writing down of a spec between us, you're the experts here on that. We can make that decision as a universal is not going to be able to do this particular feature. So what are we going to do to keep it simple, stupid?
Yeah. Okay. Yeah.
So that's where I'd like us to think, because I can do anything with PowerPoint, but I need real engineers to be able to tell me that something's a completely stupid idea. But with that end goal in mind, I think that's what I'd like to do. I mean, if the experts on this call put this together, and we find that universality is just impossible with simplicity, then okay, maybe we've got to throw in the towel on the universality side of it and decide that we need 2 different standards or whatever. But I wouldn't like to throw that one out at the beginning until we've dived into the specs and we've asked the difficult questions when we hit the roadblocks one at a time and we say, okay, that's a roadblock. That makes it too complicated. What are we going to, you know, what's the compromise?
Yeah, agree. Yeah, that's the point. Yeah.
Okay, good. Z, any thoughts from you on the story or anything else?
Yeah, Aaron, so yeah, I actually have a question when you talk about domain-specific architecture. I'm not sure what exactly means for domain-specific architecture.
Okay, no, that's fair. That's fair. So it's become a little bit of a common lexicon that, again, so the 2 gods of computing architecture are these chaps called Hennessy and Patterson, Dave Patterson, and I think it's John Hennessy. So John Hennessy is or was the chairman of Stanford computing department, and Dave Patterson is the main lead computer architect professor in Berkeley. So 2 competing California universities or San Jose universities, and they wrote a book about computing architecture way back version 1 was, I don't know, maybe in the 70s even, I don't know, when version 1 was done, probably in the 80s. Now they're up to like version 6 or 7, which they keep refreshing it. But they won a Turing Award. It's about 5 or more years ago now, maybe even, time flies by so fast, it could be approaching 10. But they won a Turing Award where they started saying, you know, we've run out of clock frequency, Moore's law's running out of steam. And so we need to just really build specific computings, you know, like with FPGAs and GPUs, we need to put the characteristic needs of an algorithm into the compute architecture itself. So you literally cut gates around the mathematical functions of a given application. And that, you know, at the simplest level, it's like some applications need a lot of memory, like AI needs insatiable amounts of memory, and it's all about memory bandwidth to the compute. Whereas traditional HPC has been just a ton of compute and has managed to make do with caching of memory because of the way HPC works. But the idea is that if you have a particular application, then you cut every gate as efficiently as possible for that one application. So you build a special computer. So that computer might be good at one job, but rubbish at another job. So, I mean, the best example is the Apple iPhone. If you look at the Apple iPhone, Apple have their iPhone processor has, I think, of the order of many tens, maybe 50 heterogeneous accelerators on silicon, as well as processor cores, as well as GPU cores. It then has things like video encoders and decoders. It has compression algorithms. It has, you know, various accelerators, and it's everything to do with whatever data comes to and leaves your mobile phone, right? Including it has camera processing because you've got the cameras, and obviously it's giving you good screen, so it's got good graphics. So that chip that Apple had designed is 100% designed for a mobile phone. And if you took that chip and you said, I was going to use it for high performance computing, you know, you wouldn't need the video encoders. You wouldn't need the, you know, a lot of the functionality that the GPU maybe, or the mix of GPU and CPU would be different. So does that make sense? So domain specific is you're building a very, very specific computer for every single application that's out there, is the idea. Does that help?
Yeah, thank you, Aaron, for explanation. So the purpose of your method is try to unify them to become one universal architecture, or?
So the proposal is, when you come to this domain-specific computing, I mean, typically it's also called heterogeneous as well. You know, heterogeneous is you have different types of ASICs that are better at one type of mathematical function than another. And that's why we have GPUs, FPGAs, CPUs, and AI chips, etc. And so at the iPhone level, all of these exist inside one piece of silicon. But it's a bit like a fractal, if you imagine. You know, as you zoom out, you just see everything repeating. So with the chiplet world, we're seeing them crush an entire server into a single package in a chiplet form. But when you build huge machines like these AI and HPC machines, you have to do the same at the system level. You have to have thousands and thousands of processors and lots of memory and lots of storage and lots of interconnect that needs to be specific to a particular application needs. And so we're in our work group, from a domain specific perspective, we are allowing an architecture that is flexible to build any type of at the system level, at the modular level, at the, you've got the chips in their packages, we can attach GPUs with FPGAs, with AI chips, with CPUs, with memory, with storage, in just about every combination you could imagine. And we can wire them together with this universal interconnect to suit the application needs at the big system level. And that's the idea. So again, I'm not sure how much you follow NVIDIA, but they've got their GPU, their old one, the last one was called Hopper. And they've got a CPU that they just created called Grace, right? And these are two different types of heterogeneous processors. And they've actually pushed both of those two together in a module called Grace Hopper. But the key thing about Grace Hopper is it's effectively got 7x16 PCI links between the Grace and the Hopper chip. And they're extremely low energy because they're only millimeters apart. And so it has a terabyte per second or near enough bandwidth between just the one Grace and the one Hopper. That's because that was good for the domain-specific applications that NVIDIA have been targeting and the AI need for additional memory and a balance the CPU and GPU for training. So their NVIDIA are already building domain-specific at their modular level, but they're targeting obviously the AI, and they own 99% of the AI training market. So it's an absolute fortune, and they make a big profit, and everything's really expensive, but it's all optimized just for AI. And so what we're doing at the system level is we're allowing us to build any type of domain-specific machine at the system level.
Yeah, so maybe we take two examples, right? So the traditional server architecture,
yeah,
and NVIDIA's accelerator, right? The GPU Grasshopper module. So how do you think the universal HPCM module, can be used for both?
Right. So good question. Yeah, go on.
Yeah, so I'm trying to, so what we are trying to create is a universal module that can be used for all kinds of the domains, right?
Yes.
Applications.
Yes.
And we see the different applications, they have different form factor. I think maybe on the abstract level, they are saying they have CPU, they have memory, they have accelerator, but when going to look at the detailed physical level, right? They are all kind of different. They have different size. They have different thermal kind of property, or the heat dissipation needs, different heat dissipation requirements. And those become physically, you have to build them differently, and to achieve maybe the cost, right? To be adopted easily by the customer. So I'm kind of puzzling what the one size of HPCM, right, can use for both, like these two architectures, and can achieve the reasonable price, or the space fit in the reasonable space, in the same chassis, kind of be adopted by customer.
Right. Yeah, no, I mean, it's a fair point. So in a traditional server, obviously a traditional server, well, first of all, your traditional server has literally been sucked all inside one single package. If you think that the HBM is good enough for the memory piece, then servers of today exist in single chips. And even including accelerators like GPU, if you take AMD's MI300A, that has, you know, a bunch of CPU cores and a bunch of and a lot of GPU in there with HBM memory. So it's like an old server with a couple of CPU sockets and maybe, you know, 5 or 10 GPU cards plugged in. So what they've done is they've crushed that entire server into a single package. So and then it's a kilowatt in power. So my point there is that the building block that everybody seems to be accepting is, you know, in 1 kilowatt type increments, and that's even going higher now, to be fair. Now, the HPCM module, we've said we want an upper limit of 1 kilowatt. In terms of power delivery, we could deliver up to 3 kilowatts, and with some of the thermal stuff we've been talking about, we may be even able to cool 3 kilowatts, but, you know, it was a case of keep it practical for now. So in terms of can we build a Grace Hopper, to your point, we could have a Grace chip in an HPCM module and a Hopper chip in an HPCM module, and we could connect those E3.S connectors as cables between the two modules, and we can easily get the same bandwidth as Grace Hopper does, albeit maybe for a little bit, another picojoule per bit of power or whatever for the extra link length. We also potentially could make a Grace Hopper module by ganging 2 HPCMs together if we didn't have enough area on a single HPCM. So we could do a double width module. And one of my other thinkings is, as TSMC with Tesla Dojo has been going towards wafer scale, I've just been noodling around the fact that you could take up maybe 6 HPCM module sites to plug a big wafer into. And 6 module sites would allow you to deliver about 18 kilowatts to that wafer. And you'd have the cooling coming into that wafer from the HPCM sites as well. So there's, you know, I mean, that's how I'm thinking about, could we go to the extreme levels? But the only other thing that in my mind is we don't necessarily, I mean, we'd like to go to extreme for the extreme high performance compute examples, but we need an IBM PC for everybody else for today's computing world, which doesn't necessarily need to be extreme. It just needs to cater for our new heterogeneous domain specific world. So I personally think we've got quite a sweet spot in terms of what we've done with HPCM. And by the way, if you do need smaller pieces of heterogeneous compute that are only sub 100 watts, then we can put them into the E3 format, and you have 16 E3s paired with every 1 HPCM. And so you can connect accelerators in E3 format rather than just media, or a combination of media and accelerators. So our heterogeneity is pretty good in that sense. And if you don't want media, but you want extra I/O, then you use those E3 connectors for extra I/O between modules, for extra bandwidth. If you're an I/O, if you want to scale with I/O, so that's the idea. Is and sure, I think you're absolutely right. We're never going to satisfy everybody. We're certainly not going to be a machine that you want to put IoT devices in. But when you think about our granularity, we could make a very good edge machine with maybe a few dozen modules, HPCMs, or we could build a frontier supercomputer with 50,000 HPCM modules, and that's a pretty wide scope. And we could, equally, we could put gaming machines or the likes, virtual reality computers in people's homes by having the homes support the 4 modules, you know, maybe one to 4 modules. And so that's a really pretty impressive scope. And then when you come down to handheld devices, etc., is when you go into dedicated pieces of silicon. but the volumes are a lot higher for those as well, right? So that's the idea. Does that answer your question or not? You're not convinced?
Yeah, and yeah, I think this is a good picture. So I think the one thing we're not answered is it's the I think the modular size, right? The whether I think we have one size here, and whether that is efficient for like all the chips, like even for
Yeah. I mean, that's
yeah.
that is an interesting one. So I agree. That's an interesting one. But in essence, if you look at the packages of these chiplet devices, they're approaching 100 millimeters by 100 millimeters now, right? So
Yeah.
can you fit 100 millimeter by 100 millimeter package on our module? Well, yes, you can. If it's just that in power, we can definitely support that order of magnitude of package. But it also begs the question, with substrates getting that big, you'd improve power and signal integrity if you actually made the entire module a substrate and got rid of the organic package and just put the advanced package straight down onto the HPCM. And then we'd get a load of budget back for our channels, and we'd be wiring, instead of having solder balls on our package, we would go straight from silicon bump to very high-speed connectors. And solder balls are a horrible interconnect for signal integrity, right? They're probably the worst signal integrity piece of the channel in today's modules. So if you could go from silicon bump to high-speed interconnect, where high-speed interconnect is effectively replacing these solder balls. If you think about it as well, like LGA packages are pretty nasty connectors for signal integrity. When like in a CPU, I believe that's partly why NVIDIA went to these modules, was soldering down their big chips into these individual modules was much better signal integrity efficient and power efficient than putting them into LGA sockets like CPUs are traditionally populated. So we're gradually moving in that direction anyway. So I think we've got plenty of mileage. And then if you have a module where if you have a module, a chip or something where our module's too small, we can then do a double width module. So we just put two HPCMs together on one big PCB. And so we can double it or quadruple it. Or if we go to wafer scale, like I said earlier, we could go to a 2x6 array of HPCMs to populate one wafer. Does that make sense?
Yeah, I think that physically you can do that. The thing is the efficiency, right? For we have like the one module, then the two module, maybe the chip is a little bit bigger than the one module, but not that far to utilize all the two module space. So maybe you have quite a bit space wasted.
Right. Yeah.
That's gradual. It's
yeah, no, I mean, obviously,
yeah.
if you look at what I guess what NVIDIA have done with their latest Blackwell is they've put two Blackwell chips in one Grace down on a very large module, right?
Yeah.
They decided, but you see, this is where I believe that's great for them, because they're doing this AI application that the whole world is it's a massive application, and it justifies the expense. But if we do smaller and smaller domain-specific markets that are nowhere near as big as the AI market, then it doesn't make sense to put three of these huge chips on one single board. It would be better to just make 3 modules and then connect them together with cables. And so because that gives you more domain-specific flexibility for different applications with those chips.
Yeah, then the question is whether those chips are able to drive that far, right?
Right. Well, and that's so this is where, in my mind, our world is in a very interesting place with interconnect. Is we always drive, or as long as history's been, we've driven roughly a 30 dB channel, right?
Yeah.
And we've improved our the various electrical interfaces to be able to drive pretty much 3 meters at 30 dBs. That's been the sort of the fixed thing, is we need to go a certain distance because of the size of racks and the size of the chassis and moving signals across PCBs and up and down cables and staying passive. So that, and now we're talking about pushing the limits to 40 dBs. Can we recover a signal from 40 to keep these distances going with with 224 gig speeds, etc. And obviously we've got the final leap as well we now have to go to silicon photonics or optics, because it suddenly makes more sense, or it's cheaper, or lower power, or a combination of all of that. But yeah, so in my mind, if you are only going a few millimeters, you might build a driver into your chips that all they can do is drive a couple of millimeters, drive to the connector from the silicon. And then if you're literally plugging an E3 module in where there's the receiving controller is only a couple of inches away, you only need 1 to 2 picojoules per bit to do that distance. And you're only driving a 5 dB to 10 dB channel. But then you say, actually, I don't want to plug a media module into this connector. I want to plug a cable in to connect a neighboring module, which is only 3 inches away, or 4 inches away, let's say. And then say, well, okay, the driver on the chip itself can only drive 1 inch. So we're going to put an active cable in with retimers. But instead of being these traditional 10-watt retimers that can take a 30 dB drive signal in and drive another 30 dB signal out, we say we optimize the drivers to drive purely twin-ax, so that literally the twin-ax cable goes straight into the driver, and you've got the beautiful clean channel of a twin-ax cable without any discontinuities. And so you say, well, wow, we can design a driver that can do half a picojoule per bit to drive 2 meters at 224 gig. Now I'm exaggerating for effect, but when your channel is so well controlled, it's just a twin-ax cable, maybe we can optimize these drivers for lowest energy, furthest distance, and lowest loss. And then on the other side of that retimer, it's a half a picojoule per bit or a 1 or 2 picojoule per bit IO. So it's a special chiplet, low energy to low energy chiplet, that means we can drive a traditional 30 dB channel with all of its discontinuities through these interconnects in PCBs and vias. We can overcome that and actually put a couple of choicely placed low energy retimers that allow us to actually do a traditional 30 dB channel that needs 7 picojoules per bit in maybe 3 or 4 picojoules per bit. And I don't know, I'm guessing, but I'm just wondering is it easier to do separate active drivers for clean shorter channels than it is to do one powerful driver over a very bumpy road of discontinuities? And you guys can probably answer that question far better than me, but so that's how. So you only put the extra energy into the cables if you need to do the extra distance, and then you can say, well, at this particular point, I need to do this much more distance, so therefore it makes more sense energy and cost wise to go optics. And as long as your universal interconnect can support these transitions between passive copper, active optics, and co-packaged optics, so then suddenly your industry has, for every cable SKU, you have 50 different cables of active and, cables that a customer can buy depending on whether they want to drive a couple of inches or they want to drive 3 meters or 100 meters or a kilometer with that same cable. Anyway, again, to Jason's point, I'm saying, wouldn't it be simple if you've got this universality? And I'm sure there's things break where it isn't as simple as I'm making it out to be.
Yeah, I think we definitely in a new domain and need a kind of innovation on the interconnection. Yeah.
Yes, right. That's right. And I, by the way, and I think the rule book needs to be torn up as well for us. You guys are forced to live by the IEEE rule books of how to build these channels and how to test them. I think in doing what we're trying to do, we may want to tear up that rule book and re-specify the rules of how do you make each piece and test it. I mean, certainly leverage what IEEE have told us over the many decades, but it's becoming a bit of a noose around our neck in my mind when I look at the IEEE rules for the industry. And again, the other thing in my mind is we've had the silicon tail wagging the interconnect dog, because interconnect and signal integrity is your domain, guys. You're the experts in this, in my opinion.
Yeah, but those IEEE standards and the IEC testing standards,
right,
are based on many years of failures.
Right.
And so we still need to be aware that we still have the physics and chemistry that we have to deal with.
Yeah.
And we also have to deal with the human factors as well that go along with the ability to plug these things, the ability to lock them in place, the ability to drop something on the floor.
Yeah.
So to say just because they're inconvenient, which they are, for the last 40, 60, 70, 70, 80 years, as these things have moved forward, evolved and changed, used to be that at no point do you go less than 100 grams of force at your interface. And now we're down into the teens and 20s, left over from the old Bell Labs AT&T 40-year life.
Yeah, I think you eloquently put it really well, Howard, because to your point, what's happened is these things have been learned over many years, right? And it's a case of we've all forgotten what we've learned. But now everyone is so scared to deviate from them because will we lose what we learned back then?
Well, we all have, and Jason and Z will say as well, we have had a lot of failures.
Right.
And my dad, who was a Bell Labs guy for 50, 60 years, will say once the electronics work, we just wait for the mechanical stuff to fail.
Right.
And so all the dreams of having these things modules, and if you've ever had to deal with a 2-inch long cable, you still have your 1-inch wide thumb to deal with that.
Yeah, no, I get it, but I guess my only contradiction to that is our servers are getting more and more stuff full of cables, and everybody hates cables because it causes us no end of grief when it doesn't work properly.
If you have the backside of a rack and you look at the number of cables and the number of 200 cables
right
that get jumpered all over the place, you're at a point where the racks, the airspace behind the rack has to be made larger just to accommodate the thousands and thousands
Right.
of twin-ax lines that go from server to server to server to server to power supply.
Yeah.
And then the power supply, you end up with a 1/4 inch by 2 inch chunk of aluminum that has to go the length of the rack in order to carry the amount of power. And there is the interesting part of this particular conversation we've been having here for the last few months is that the modules and the scale have changed from a 19 or OCP size rack to a handful of decks of cards.
Right.
And the amount of energy used in that 19-inch rack, enough that each of these data centers has to have their own wiring or power center just to keep them powered.
Yeah.
So and we've got to move hundreds and hundreds of gallons of liquid just to chill it, even in non-liquid applications.
Right.
So the real point here is the chemistry and physics. We have pushed the limit, and I would have said this 20 or 30 years ago as well. We've pushed the limits of chemistry and physics as far as we can. And of course, in the last 20 or 30 years, we've pushed it that much farther.
Right. Right.
So if we're going to make these disconnectable and connectable, being applied with people with fat fingers, we have to remember that those IEEE or EIA testing guidelines, whether it be for vibration or earthquakes or rolling the rack across the floor vibration, there's a whole host of things that can occur that will cause these things to fail. And as smaller and fragile.
I guess, yeah, like I say, that all those learnings, I get it, right? And I guess that the trouble is those things also become nooses around our necks that stop us from moving dynamically. And it's a case of, can you move on, like without don't throw the baby out with the bathwater. It's a case of, we need to do a different way, but what do we make sure we don't forget from all those learnings whilst redefining how we go about it? And so a couple of your, like, rolling racks, like, you're going to build the data center in place with HPCMs. The only thing that will get delivered to a supercomputing room will be these HPCM modules. So you're not rolling any racks. You're just plugging a module into a wall. What if we only had gantry robots plugging in the cables in and out, and there was no human doing it? So it was a very precise, accurately controlled, pluggable. I'm only giving a couple of examples, Howard, but I guess that's or just the way we've actually done this. Yeah, it's you're obviously, you can't make an omelet without breaking a bunch of eggs. So I'm sure we're going to forget a lot of those wonderful learnings and have to learn it again. But a lot of those learnings from 70 years ago are not even applicable today, but they're probably still in the rule book because everyone's too scared to throw it out of the rule book. So it is a challenge. I mean, your point is extremely well made, and I guess that's the reality why incumbents, like in the car industry, like GM and Ford, don't want to throw things out on these, tremendously vibration, heat issue, interconnects on automobiles must be the biggest nightmare ever, right? And yet Tesla comes along and throws everything out and starts again. And I'm sure they've had a tremendous amount of pain by making mistakes that were solved by the traditional ways years ago. So yeah, I get your point, but that's one of the challenges with innovation versus evolution, right? Or radical innovation versus evolution, revolution versus evolution. on that note, well, a good discussion. Hopefully, it's encouraged you and not put you off. But in terms of us battling down this universal interconnect avenue, would you agree? Just as a quick poll of the three of you, are you more skeptical or more after our discussion today, or happy to take on the challenge?
Well, I've certainly learned a little bit more about computer architecture.
Okay, that's good.
Yes, I think the universal interconnect may be possible, but certainly I'm on the connect side, so cable connect side, so maybe it's more easy for me to visualize that. But universal of the whole architecture, that seemed to me I couldn't reach that. So.
Okay.
My feeling is that there may be multiple universal interconnects.
I'm sure there will be, yeah.
And certainly if there's power, signal, and loss that we have to deal with, and in this case especially size to be managed.
Yes.
We have to pack a lot in a little space, and has been the first sentence of every presentation that has been made by the interconnect industry since 70 years ago. So right now we have manufacturing technology that I find astounding that they're able to do the things that we've been able to do in interconnects. So that is no reason that more astounding things can't be done in the future, and will be. So, but if you have to carry 30 amps, you don't want a 14 gauge wire.
No.
You want a 12 gauge wire, right? So we're stuck with that chemistry and physics as well. Unless we're going to do, superconductor absolute zero, where we're able to manage those things down to dealing with the physics and chemistry of copper, aluminum, and solid gold wires and that sort of thing. So I don't want to be discouraging, but I think our universal connector is going to end up being less universal and more application specific, just like the chips that we were talking about here.
Okay. Well, yeah. Yeah. Okay. Maybe it's a family of
yeah. Oh, I'm all for a family of things. Yeah.
In the same, I think that's probably what I'm alluding to.
Yeah, and it's like
I think the proof will be in the pudding, right? I mean, if we've got to start putting pen to paper and then seeing what the roadblocks are to that universal interconnect, and then then seeing how that pans out, I guess.
As all three of us that are on here with you have seen hundreds of applications where somebody comes along and says, well, I actually need 2 more or 10 more lines to carry
I know. Well, that's where you do need that extra compromise, right? So
yeah, it's like, okay, that was great for doing this, but I need 10 more.
Yeah, no. Yeah. And then they have to go off and do their own thing, right? I mean, at the end of the day, and yeah, no, fair enough. All right, guys. Unless there's anything else, we're a little bit over, so I'll call it a wrap. It was good discussion, though. Thank you very much for the input.
Alan, would you post the summary?
Yeah, I always do. So if you look on the wiki, you see our previous interconnect discussions. You will see a link to the Zoom video. and you'll see a link to the minutes, and I paste in the AI summary into the minutes now. So you'll be able to see those as well.
Yeah,
But-
okay, we will check.
Both previous meetings and today's meeting.
Mm.
Now,
Yeah.
by the way, just word of warning, the AI summary can get the wrong end of the stick sometimes. So,
Right.
but it's not too bad to get your general gist. And also, the Zoom link should give you access to a full transcript if you had a so desire to cut and paste a full transcript. And that is pretty damn good at understanding everybody and converting that into text. So that's there as well on the Zoom link.
Okay.
All right, guys. Well, thanks very much for a very engaging debate. Much appreciated.
Okay, thanks.
Okay. Alan, thank you. Z, Jason, have a
Okay,
good day.
bye-bye. You too.
Thank
Bye.
you, Alex. Thank you, everyone.